Okay, I'm just going to record this is for a student who can't be here. Technology issues. Yep, you're skipping to the slide. We are not going to, we're going to do titrations on Wednesday. So I know we had a reading assignment. I didn't want to change anything last minute for that. So I'll change the assignment so that this assignment will publish today at 5. And then the titrations, I'll just extend. So if you want to start attempting titrations, you can, but I'd like you to work on solubility. So I'll just extend both of them. Is that cool? Okay. So solubility, the cool thing is it's the same thing we've been doing with equilibrium. So we've mostly been talking about acids, right? Acids and bases being, if they're strong acids, they completely dissociate. That's also a strong electrolyte, right? Because they're dissociating into ions. And ionic compounds are, by definition, kind of electrolytes. So they're going to dissociate as much as they possibly can. And you remember when we learned about, remember when we learned about solubility rules, like this plus this always dissolves, or this plus this never dissolves, that kind of stuff. This is the numbers behind it. So how much does it really dissolve? Because there will be things that'll be harsh, slightly soluble. And I always hated those because I'm like, what does that even mean? Well, this is the numbers. So when we write the solubility equilibria, we're basically going to have my little tablet. We're going to have a solid compound dissolving into its ions. So. Sorry. Come on, dude. Okay, so I'd have something that's XY solid going to, well, equilibrium arrows, of course, going into X plus aqueous plus Y minus aqueous. So that's kind of the gist of it. So we always have solid reactants and going into ionic products. So we call this, when we write this equilibrium, we call it the KSP, or the solubility product constant. And again, it's going to be products over reactants. So for this fake compound right here, what would I write for the KSP? Somebody who's brave on Zoom want to tell me. Again, it's always, products over reactants every time. Mariah, yes, go.
The concentration of X plus times the concentration of Y minus.
Yep.
Over, no, what?
Yes.
Put solid on the board.
No, you don't. Good. Over nothing, because 1, right? Because of solid. Good. You caught it though. But we would write over our product, our reactants, but our reactants are always going to be solid. So it's just going to be our products. So it's kind of nice, right? So, so they're going to have a different types of solubility. If we have a high amount of solubility, we call that soluble compound. A low amount, we call that insoluble. That's just kind of a classification. Where they draw the line, I'm not actually sure. That's a great question. Where do you draw, what's the cutoff? Maybe we could look that up. Actually, that's a good question. So far, questions. Does this make sense? I'm only looking at a specific 4 of you at a time. So far, so good. Thank you, Mariah, for jumping in there. Okay, great. Okay, so let me end that, clear that up. Okay, great. So the KSP. And I don't even like this. It's fine. It's fine. Okay, if we have the reason I don't love this is because I feel like it's a bunch of memorizing. And I don't want you to memorize. I just want you to break apart stuff. So if I have a metal and a non-metal coming together, right? We put them together with their charge. So if I have, calcium and let's say and fluoride, how many calciums and how many fluorides would I need to make calcium fluoride the compound? What do you think? I know it's more awkward in Zoom. How many, you can hold up your fingers. How many calciums? Yay, how many fluorides? Great, thank you. Okay, good. So I need calcium, 1 calcium, 2 fluorides to balance that out, right? That's how I'd write my ionic compound. So then when I break it into ions, again, you said I had 1 calcium. And it would be the ion, so it'd be dissolved. And I had 2 fluorides. So you take however many is your subscript, and that's what goes out front. And you take, so again, subscript goes out front, and then our charge is just whatever the charge happened to be. Yes, okay, cool. And we write it in the aqueous form. So again, so that's how we would dissociate the reaction. And then how I would write the KSP is just my products raised to their coefficients, just like we did with regular equilibrium. So, you know how like, I'll let you finish writing. You know how before with like weak acids, how could we tell how strong a weak acid is by looking at its Ka? Like, how could you tell who's stronger than another? You could type in the chat too. Oh, thank you, Marcus, in the chat. Yeah. I'm just saying that. How could you tell who was a stronger acid when you look at their Ka? Yep, bigger Ka, thanks Chris, bigger Ka, closer to 1, right? Larger the Ka, thanks Quentin. The stronger the acid, right? And smaller the Ka, the weaker the acid. And same thing with Kb. With KSP, we actually can't tell the solubility just by looking at KSP. So I'm not even gonna, we have the KSP as a reportable value, but it doesn't really tell you directly the solubility. The solubility, which we know is the amount of solute that will dissolve in a solution at a certain temperature. We've talked about that with solubility before, right? The maximum amount of solute. And we've normally talked about it in molarity, so the molar solubility, so the amount of moles that will dissolve in 1 liter. That's pretty normal. And when we reach solubility, we're saturated. Remember that? And then remember unsaturated and supersaturated, those fun things. So this solubility is that limit when you've hit that saturation point. Okay, and what I'm going to show you an equation, and I just want you to know that you don't need to, please don't memorize this equation. The general thing is, you remember how when we do an ice table, we find X? Yeah, X is the solubility. Okay, so when you do an ice table and you set it up for KSP, and normally we found X before for weak acids, and that was like our hydronium concentration. This X is our solubility, our molar solubility, because we're always in molarity here. So I'm just going to write that molar. So solubility equals X in the ice table. So once again, I'm going to show you this equation that looks awful. Right, this doesn't look fun. This is not good for anybody. This is technically what you're going to end up doing, but so you're going to get there, but it's just finding X. And you don't have any denominator, which is really nice. So you're just going to find X. So yeah, we'll put this equals X. And that's technically what you've been doing this whole time. This is X. Not fun when you look at it like this, but you've been doing it, the process. Okay, you ready to go practice? I think it's time. Okay, so let's do barium sulfate. We're just gonna try writing out, damn it, the KSP. Okay, so here barium sulfate, note one, nope, I lied. One barium, one sulfate, right? So when I look at that salt, you're gonna need to dissociate it and know one barium, one sulfate, know the charge. Look it up if you need to. So then when I do the KSP, we're just gonna do barium raised to the first power, because that's a coefficient, times sulfate. Raised to the first power divided by 1. So that's our expression. Okay, ready for another one? So there's a KSP. Okay, let's do one together, and I'm gonna have you guys help me out, so someone get brave. Okay, now I have barium phosphate. So here's the compound, give you the formula, give you the dissociation. What's the KSP for barium phosphate?
I can go again.
Okay,
It's the concentration of barium raised to the third power,
great.
and then the concentration of phosphate raised to the second.
Great.
Over 1.
Over 1. So those become the coefficients, and then we just put our ions, raise those coefficients. Okay, good. Mariah, you would have thrived on Zoom. Maybe you did. Way to go. Okay, great. Barium cubed times phosphate squared. So like I said, KSP is not solubility. Solubility is the maximum amount that will dissolve. But KSP, so unless our compounds dissociate like a 1-to-1 ratio or 2-to-1 ratio or whatever, they have the same kind of dissociation ratios, we can't compare KSP. So the best thing to do is to look at the solubility again, which is X. We could use grams per liter, technically. Like, I don't know if you remember that one chart where it was like, this was temperature, and this was solubility, and it was in grams per 100 milliliters. That's another one. That's basically grams per liter. So that's a common one, right? How many grams can dissolve in 100 liters or 100 milliliters? But we'll use the common one we're going to use is molarity, because that's what goes in here, right? We're using concentration. So we could use KSP and go into an ICE table to get the concentration of each ion, right? That would be the E section. And then find out what X is on its own by dividing by the coefficient. And then you can use the molar mass to go into molar or mass solubility, so grams per liter. But honestly, the way we're going to do it is you're going to be living in this area. Mostly there, because this is like in between KSP and solubility is where we're going to be. Okay. Yeah, I'm going to have to look up what that index is. Okay, so we have calcium fluoride. So while you guys help me with this, we can, I'll look up the values. And I'm actually not going to make you look up the values right now. We're going to get another one where we will look up values. So the calcium fluoride, now in this, how many calciums are there? You can show me on your fingers. How many fluorides are there? Good, that's the number that goes out front. So we're going to have calcium fluoride solid goes to 1 calcium, 2 plus. Oops, I'm going to actually put phase aqueous plus 2 fluorides aqueous. Okay, so then KSP equals concentration of calcium times concentration of fluoride squared. Okay. I'm strongly tempted to put you into breakout rooms. So you can practice the next ones together. I know, I have, yes, Krish.
How did you figure out the charge again for calcium?
We just look at the periodic table. Also, I know that I have fluoride is a -1, again, from the periodic table, and I have 2 of them, so calcium must be +2. Definitely using the periodic table as our guide on this whole chemistry journey that we are in this semester. And onward for you, because I know you're gonna take more. So use your periodic table, it will help you. Okay. Let's pause the recording. Okay, so how was the Zoom breakout room? Seems like it went okay. Okay. Okay, what'd you guys get? Does anybody want to volunteer to do A and B? Maybe someone who can write on their device. I know that
I
someone.
can, Tasha.
Okay, thank you. Whoops.
Can I share my screen?
Sure, yeah,
Cool.
that makes it easy.
Give me a second. Okay. 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 So the first one was barium carbonate, which is a solid,
Mhm.
and it dissociates into barium 2 plus carbonate 2 minus. Those are both aqueous.
Cool.
Should I do the second one?
Well, what's the KSP for that then?
Oh, yes. KSP will be barium 2 plus and carbonate 2 minus, the concentrations of those.
Cool. Anybody have any questions? Get something different? Feels good. Excellent. I'm gonna do a reaction because I can. I'm gonna do a clap reaction
Yay.
because I am so proud of you for being so brave. Does
Yay.
anybody else want to potentially earn a clap reaction from me? Okay, apparently not. No, nobody wants to? Oh, Quentin went for it. Okay, so Quentin, did you get, when you dissociated, you got 2 silvers for 1 sulfate?
Yep. The
Excellent.
charge of silver is normally 1. That's what I did. I don't know if you can read what I wrote because I can't write on my device, but
You're good. I do know what you mean. Oh, dang. Well, I will write it because I can. So we have silver sulfate. Hardest part of this is remembering what is silver's charge and formula and what's the charge of sulfate. So we have silver +1 and sulfate, whoa, -2. So then I'm going to need 2 silvers for every 1 sulfate. And then we don't write our charges at the end. Well, we do later, but then we get 2 silvers and 1 sulfate. And so our KSP is just what Quentin put, silver squared times sulfate. Oh, to the 1. Cool? Thumbs up from my friends. You guys all good? Okay. Let's do some things with numbers now. Okay, so let's calculate that solubility. So again, solubility is what? You can do it with your fingers if you want. Do it, everybody do it. Bronwyn, I'm looking at you. You're not doing the X. Thank you. Fiza, what the heck? Okay, thanks. Oh, there's Kara. Great, I saw. Thank you. Okay, great. So here is calcium fluoride's KSP, it looks real small, right? 10 to the negative 11, but once again, it does not tell us the whole picture. So what is the molar solubility? Oh, and I know we have like numbers, right? It's like, don't worry about the numbers. I don't like the numbers. I'm sorry. I'm going to take them out of next year's notes. I don't like it. So what do we always do first? You've already done it so far. What do we do?
Write out the chemical equation or reaction.
Yes, we write out the expression or the reaction or write the equilibrium thing we have going on. So here we've done this already. We have calcium fluoride dissociating into its ions. Okay, great. And we could do one of two things now. What are those two things? You have like a 1 and 2 shot. Either one's right.
Write out the KSP expression.
Write out that expression. So we'll do what we did before, right? Everything you've already just practiced times fluoride squared. And then what's the next thing we do before we start to solve for things? We've done a lot of these. Involves a table, certain kind of
Ice.
table, ice table. So now we're gonna write our ice table. Now, what thing do we not care about? Because it's a pure substance.
The calcium fluoride.
Yeah, we don't have to care about our reactants. Yay. Now, technically, we have some reactant that's solid and it is being dissociated into a solution. So we are technically losing some, but it's not part of our KSP expression, so don't really care. Just know that. So how much of my products do I start with? You can do it on your fingers if you want. 0 products that we start with. Now, this is where it's a little different. We were real lucky with our weak acids. Maybe we didn't feel lucky, but we were because they were a 1-to-1 ratio. In this case, we're not a 1-to-1 ratio anymore in this one instance, right? I have now, I'm going to add X for calcium, but what do I have to do for fluoride?
2x.
Double it.
Yes, perfect. To both of you who spoke, yes. 2x, because of that 2 right there, we have to put a 2x. So whatever you happen to do for that out front, however you balance that dissociation, that's the number that's going to go in front of the x. It's also the number, whoa, that goes, it's squared. Do you like that arrow? I was winging it. So we not only have to take it into account in our ice table, but also in our expression. Okay, so it's gonna, the factor for fluoride is gonna be doubled and squared. So don't want to mess that up. Okay, great. So then at equilibrium, we have X and 2X. And then we just plug that into our KSP. Now we know KSP, the value is 3.9 times 10 to the negative 11 equals calcium is just X, and then fluoride is 2X. And then I have to square it. Honestly, that's probably the hardest thing you're going to have to deal with in this is remembering to double it and square it, or triple it and cube it, or quadruple it and raise it to the 4th, right? That's going to be the hardest part that I've seen. So now we need to square both the 2 and the X. So what's 2 squared? 4. And what's X squared? X squared. So we have X times 4X squared. So that equals 4X cubed. And that equals our KSP. 3.9 times 10 to the negative 11. So how do I get it by itself?
divide by 4.
Yes,
First.
thanks, Emery. Divide by 4 and cube root, good. Now, for those who have calculators that do cube root, cool, but also keep in mind, we're gonna go higher power than cube, and a lot of calculators will do cube root. But higher than that, it's kind of trickier. So what you can do, you can cube root it, that totally works. Cube rooting is the same thing as raising it to the 1/3. So whatever we raise it to here, we could just raise it to that fraction, 1 over that. And it will undo it. So just keep that in mind for the future. Get my calculator. Have the calculators ready? I can't see, so I'm gonna just get out your calculator. You ready? Taylor, you got your calculator? Boom, there it is. Perfect. Okay. So, whoa. 3.9 times 10 to the negative 11 divided by 4 to the 1 over 3. What'd you guys get?
I got 2.14 times 10 to the negative 4th.
Excellent. That's the molar solubility. If I wanted the mass solubility, then I just realized that this is in technically molar is moles per liter. So then I could just divide or multiply, I mean, by the molar mass of calcium fluoride of the whole thing. Okay, we're going to practice that later, but that's how I'd go to the next step. So this is correct. This is the molar solubility of the compound. If I wanted to know how much calcium is in there, there's that much. If I want to know how much fluoride is in there, there's double that, because 2x, right? So plug into your ice table as needed, but that's technically what the molar solubility is. Does that make sense? We could do things with it from there, but that's how we get that, just solve for x. Okay. Let me clear that. Okay,
Hey, Tasha,
yes.
you briefly just go over how to find the charge from the periodic table? I know it's like from the top number. So like if it's like the far left, 1 or 2, it'd be a positive. What about like ones that are like in the middle or
Group 1, group 2, +1, +2. Noble gases, none. -1, -2, -3. In here, you have to figure it out based off the charge of your nonmetal. That's why they're transition metals, except for aluminum, zinc, silver are 3, 2, 1. Whoops. 3, 2, 1. Those ones are always that. Does that help?
it'll probably take some practice, but yeah, I get the gist of it.
Definitely some practice. Okay. So we have solid silver chromate, and first of all, whoa, anybody feel overwhelmed by this amount of words? Too much. But they're basically telling you that you have reached solubility. So, right, we put the solid ionic compound in the water. And when you know that some of it is still undissolved, you know the solution you have above it is saturated because you cannot get any more in there. And then they let it sit for a long time, several days. Seems excessive, but it's fine. They're doing an experiment. Analysis shows that silver ion concentration is 1.3 times 10 to the negative 4. Assuming that silver chromate is saturated and there are no other important equilibria, calculate the KSP. Oh, yes, I like this one. Okay, what's the first step? What do we do first before we do any calculations?
Write the equation.
Ooh, we're gonna write the equation. And they even tell you the compound, so you don't even need to remember what chromate is. That's good, because I don't. No, I can't, I don't remember the charge. It's okay, so we know silver. Chromate, solid. Dissociates into how many silvers? Show me on your fingers. Hold on, I'm gonna look at everybody. Yep. Okay, wait, how many silvers? Good, Taylor, see. How many chromates? I saw that, Spencer. I was just watching it. Oh, good, yes. Good, 1. So we have 2 silver. And 1 chromate. Good, okay. Now, I like to just do the KSP expression. So we have silver. And I would actually, if I were you, do it first, because sometimes if we wait, we'll forget to square things, like, especially like if it's a quiz or an exam and you have to like keep things straight, it's easy to forget. So we'll square it and then we'll write that first expression. Cool.
Is the chromate supposed to be 2 minus? That's what it shows in the
It
like
is.
prompt.
It
Okay.
is 2 minus, and thank you for writing that. Or for saying that. It is, and see, I told you I was gonna think it was 1 minus, and I did. Even though I noticed it. Thank you. Okay, so now we can do our ice table. We don't care about silver chromate, solid. And then it tells us, so what are our initial amounts? I wish I could see more of you. I only see like 4. It's a lot of pressure. What's our initial amount? Oh, good, Taylor, thank you. 0 in this case. So then, key thing here. So silver will go up, we would theoretically have a 2x, right? And 1x of chromate. But we know silver's compound concentration is 1.3 times 10 to the negative fourth, I mean. We know that value. So what do I need to do to get how much chromate dissolved?
Do you take half of it?
Yep, it'll be half. Because we know that silver goes up, oh, you can't see that, by 2. And so if that's how much we have, then we're going to have half of that amount of chromate. So we'll have, what is it, 6.5? I think it's 6.5 times 10 to the negative 5. That's how much chromate it should have. So half of the silver. Does that make sense? I got 1 nod, but I also can only see 5 people. Okay, wait, go on to yourself and do, damn it, how do you do this? You used to be able to like reactions, thumbs up. Damn it, can you thumbs down? There's way too many reactions now. I got 1 thumbs up. It's fine. Do you guys get it? Is it okay? I'm spending way too much time on this. Remembering Zoom. Okay, so then now we're gonna plug it in. Okay, you can react yes or no. Okay, I will ask you to react yes or no. You don't get it, Krish? Or you're just trying things?
I'm
You
just proud.
Okay, thanks. Okay, so we'll do silver's amount squared times chromate's amount. And we're gonna do it. I'm doing it with you. Whoops, 1.3 times 10 to the negative 4 squared times 6.5 e to the negative 5 What'd you get? I thought you were showing me, Taylor. I was like squinting. Here, I'll show you. Can you guys see my calculator? It's poor quality, a lot of glare. Can you see it? 1.1 times 10 to the negative 12. Did you guys get that? Okay, cool. See it. Good. Thanks, Ellie. So KSP 1.1. Okay. So see, it's like kind of complicated in the sense of like KSP doesn't have a whole lot of meaning because it's like, okay, which thing has what concentration? And if this was a 3, then silver would be super impacting the KSP value and it would be even more. So KSP is not a super good indicator of like solubility in the way that acid base was. Okay, so saturated solution of magnesium hydroxide. Notice how many hydroxides are there? It's in the formula. How many hydroxides? Oh, hi Archer baby. Cute little baby. Okay, good too. pH of a solution is found to be 10.17. If I know the pH, what can I find easily? Good, I saw that, Krish. pOH, good. And so I can then find hydroxide concentration at equilibrium and then find magnesium. So I'm going to put you back in your breakout groups. If anybody has an issue with their group in the sense that your person is like MIA, then let me know. No, I'm not. Okay. So you guys feel okay with that? Okay. So then the tricky part here is that they didn't tell us the concentration you have to solve for hydroxide. So we know pH, pOH equals 14 minus pH. So minus 10.17. So that's 3.83. And then hydroxide concentration equals 10 to the negative 3.83. I'm gonna let you pause right here and see if anybody needs help or like, was there confusion here? There maybe was, but maybe you're feeling okay about it now. That's the tricky part. Now this, what is that value? Anybody have it? Want to throw it out?
We got 1.48 times 10 to the negative 4.
Great, that sounds about right. Okay, good. That's what goes here. That's the hydroxide concentration at equilibrium. It starts out with 0 and it goes up to that. But notice this is plus 2x and this is just plus x. So then over here it should be what?
Half of it.
Half of that. So I think it's like 7.4.
7.4 times 10 to the negative 5.
Sweet. Dude, my mental math right now is like coming in handy. So that's what's going to go in here. So KSP, nope. Okay, there we go. KSP is going to be 7.4 times 10 to the negative 5 times 1.48 times 10 to the negative 4 squared. I don't know what that is, but I guess I can look it up. Okay, 8.48 squared. Did you guys get 1.62 times 10 to the negative 12? I got Taylor with a yes. Anybody else? Okay, got a couple more yeses. Okay, Stephen with a nod and a mustache. It's looking real full today. Did you do something different?
Oh, I just woke up like this.
Oh, how lucky. It's just there. It's good. Okay, so that is 1.62 times 10 to the negative 12. Units? No units, no units. Okay, we're still happy about that, no units. Okay, we're gonna skip this one. Are you guys feeling okay about it? Or do you need this? clear. Do you need this? Are you ready to move on? Okay. This is not the right work. I'm working on videos. I just made the second to last acid base one, so I'm working on it. I'm sorry. Okay, this is KSP. We've done it. We've done solubility. We've solved for X. We've solved for we've solved for KSP with the concentrations. Key thing here though, so this, I changed the problem to not be calcium fluoride, but to be lanthanum fluoride. It's fine. Key thing, once you solve for X, we got this before, when you go between molar and mass per liter, use the molar mass of the whole compound. Okay, so if I was doing calcium fluoride, this is the molar mass of calcium fluoride, the salt. Okay, that's the key thing. Okay, I want to make sure we get through this lesson, so I'm going to keep going. Okay, you guys okay with that? Okay, so factors affecting solubility. One, common ion, just like we had it with when we learned last time about buffers, before buffers, right? One, if I add some of the common ion, it makes it shift away. So maybe I have an equation. Nope. Okay. So for example, if I have, I guess I'll use calcium fluoride here. Calcium fluoride going to calcium and fluoride. If I add a bunch of, okay, I've dissociated, right? I have my X and 2X, and I found out how much I make. If I was to add a bunch of fluoride for my initial, right? Think Le Chatelier's principle. If I have a bunch of this, I'm going to shift. Oh, let's see if I can do the arrow that way. So I'm going to actually get less. So if I have a bunch of fluoride that I added, I'm now going to get less calcium dissociated than it would have originally. Okay, so if I have either calcium or fluoride, the whole thing will be less soluble. So what's the molar solubility of calcium fluoride in 0.1 molar calcium nitrate? So who's my common ion here?
Calcium.
Calcium's the one. So yes, if you see, for the most part, you see group 1, okay, alkali metals, remember sodium, potassium, lithium, we don't care about them, remember, because they always break apart completely. Same thing with nitrate, always 100% of the time breaks apart into ions. So if you see group 1 or nitrate, just know that it's not contributing at all. It's going to, so calcium's the thing here we care about. So let's write our thing. So I'm going to write the dissociation of calcium fluoride, just like I've been doing. Right, same principle. I'm going to even write my KSP down here. So calcium times fluoride squared. So I'm going to fill in my ice table. Now, instead of writing a 0 for calcium, I'm still going to do it for fluoride. I'm going to write 0.01 molar coming from this guy. So now I'll still add, I still need to add some. I'll add X and I'll add 2X. But it's going to be a different X. Hold on, I don't have my, okay, and there's that KSP value, 3.9 times 10 to the negative 11, that's what I needed. Equals, so I have 0.01 plus X, whoops, and 2X here. So I'll have 0.01 plus X And then 2x squared. I'm thinking we probably get to do get rid of a plus x. Yep. Okay, sorry about that. So just like before, this is a pretty high concentration of calcium compared to how much dissociated. And we're gonna be shifting even more that way. If you want to, we can do the whole route. It's up to you. But I'm going to make the approximation that plus x 0.01 plus x is gonna be so small because I'm gonna be dissociating even less calcium over than I would if it was by itself, that I'm actually just gonna write this as 0.01. I'm not gonna put the plus x, and then I'll do 2x squared, which is 4x squared. So now when I solve for x, I'm gonna divide by 0.01 and 4. And then I'm gonna square root it. So hold on. I get 3.9 times 10 to the negative 11 over 0.01 times 4. And that equals x squared. So then I square root it. So let's do that. So 3.9 times 10 to the negative 11 divided by 0.01 divided by 4 square root. And I get x equals 3.1 times 10 to the negative 5 molar. Now flip back a few slides. I actually don't remember what they, well, here it is. Here it is. KSP before. This is actually the exact same problem. When I didn't have 0.1 molar, there it is, right? We divided by 4 cube root. We get 2.1 times 10 to the negative 4. So you can see I decreased. So it was 2.1 times 10 to the negative 4. Now it's 3.1 10 to the negative 5. So it has decreased by a factor of 10, my solubility for this compound. Does that make sense? You could do the plus x and then you'd see it should be about the same. But there's no hard and fast rule about that one.
Did we take away the plus x because we divided the 0.01 by the 3.9 times 10?
So we got rid of
11?
we got rid of the plus x. I'm glad you asked, because we're going to dissociate such a small amount. So look, if I go 0.01 plus what the x I found, 3.1 e to the negative 5, I get 1.00312 times 10 to the negative 2. So I basically have the same number, right? I have, so whoops, wrong thing. 0.01 plus 0.000031. That's what I'm adding. So this number is so small compared to this number that I basically still have this guy left. That's why I get rid of the plus x there. So I just made the approximation basically, and I got rid of it. So right here, that and that are the same thing. I just went down a line. And then I divided. So it could almost go like that. I don't know if that makes sense. Let's keep learning. Math wise, hold on, I'm gonna look at you. Math wise doesn't make sense. Okay, got some, maybe not super convinced, but Anisha's had an enthusiastic nod. Thank you. Oh, and you had a plus, a yes. Okay. Let's do manganese 2 hydroxide together. We're going to calculate the, oops, let me clear this. We're going to calculate the molar solubility of manganese 2 hydroxide, and it contains 0.02 molar sodium hydroxide. So who's my common ion here?
Hydroxide.
Oh, thank you. Okay, So let's dissociate manganese hydroxide. So I'm gonna have manganese 2. So Chris, here it tells you the charge is that +2, by the way. If you're a transition metal, +2 hydroxides. And then we have our KSP equals manganese times hydroxide squared. Cool. Okay, now what do I gonna, don't worry about the initial or the reactants. Okay, initial, what is it for manganese? I see a cat tail. Cute cat, Stephen. What is it for manganese? Initially. Show me with your fingers. Okay, cool, 0. Okay, and then hydroxide is right here. So it's 0.02 molar because I'm bringing in hydroxide. Okay. So then I'm gonna do plus X plus 2X, X, and 0.02 plus 2X. So, and this is a really small number. So we're gonna do 1.6 times 10 to the negative 13 equals manganese, which is X, times hydroxide, 0.02 plus 2X squared. Now, do you think it's likely that we'd probably get rid of the plus 2X? Yeah, because I don't want to solve that. Do you want to solve that? Could we solve it? Quadratic formula for sure, but like nobody's got time for that. So do you just bank on the fact that we're probably going to make approximations most of the time in my class in this next test because I prefer that. 1.6 times 10 to the negative 13 equals X times 0.02, and I'm going to get rid of the plus 2X. I'm just going to square. I'm just going to get rid of the plus 2X. So then what would I do to get X by itself? This one's actually very easy. Now. I see you all solving, so I'm going to assume you know what to do. Divide by 0.02 squared. So we get 1.6 times 10 to the negative 13 divided by 0.02 squared. Did you guys get 4 times 10 to the negative 10? Sunny did. Got Kara did. Do a thumbs up for me. I like those. You can do a yes. Taylor did. Okay, good. So X, which is our solubility for the manganese hydroxide, is 4 times 10 to the negative 10. I'm going to assume that's a lot smaller than it would be on its own because that's pretty close to this KSP value, which would have to be. I did open the attendance for today. It published maybe 8 minutes ago, and it's asking about Zoom. It's also reminding you about exam 2 corrections being due on Wednesday with no exceptions. Unless you have had a significant emergency and you know who you are. If you've been like going through some things and communicating with me, and we can talk, but most other folks it's due on Wednesday in person. Unless there's a storm, but I hear it's going away by Tuesday, so.
I have a quick question.
Yeah.
So yes, we're doing the X is small, and you said we'll do it most of the time. Even on that one we skipped. Anyway, it had like wasn't exactly the same, but if you're cubing a number in there, that number turns into something pretty quick. Like it could be 27x. Are we going to just keep on crossing it out, or eventually we have to start using it?
At some point, you probably do have to start using it. This is a pretty, like, right, if we did that X here, At some point you probably do. In this class, we're not gonna get to it. Like, it's not gonna get to like be a factor we have to worry about too much. And I would have to calculate that for you. So I can. Great. Here comes my clock. Okay. Okay, we're gonna keep going. So we talked about common ion, now pH. pH, basically, if my ionic compound has something that can react with either an acidic solution or a basic solution, which if I have an acidic solution, what do I have a lot of?
Hydronium.
Good, a lot of hydronium. So if I have something that can react with hydronium, then it will. If I have something that can act with hydroxide, then it will, and that will affect it. Okay, so here I have a salt. Now its anion is lead fluoride. This, one of the ions, fluoride, is an anion, right? That's a weak base. It came from hydrofluoric acid. So if I add H+ to this solution, I'm going to actually force a bunch of these fluorides to react. And now they're not going to be, right now I'm basically pulling fluoride out of solution. Because now they're attaching to the hydrogens if I add a bunch of hydrogens. So I'm going to lower the fluoride concentration if I do this in acidic solution. I lower the amount of fluoride ions there are because they're going to react as a base with the acid. And so now I'm shifting my equilibrium, so I have to make more fluoride because now the fluoride's actually been removed. Over here, lead iodide. Now is iodide, okay, think about hydroiodic acid. I'm gonna pull up you guys. Hydroiodic acid, what kind of acid is that? Weak or strong? You can type it in the chat if you want. HI, weak or strong?
Strong.
I heard it. Strong, it's strong. So remember, conjugate bases of strong acids are?
Negligible.
Yes, negligible, good. It's way easier to do those call-outs in class in real life, but yes, they're negligible. So basically, iodide over here, it doesn't care if there's hydrogen ions. It can't produce an acid. It's gonna just completely dissociate. So if I have, so basically, if my anion is the conjugate base of a strong acid, right, negligible, then it doesn't matter about it's not going to be affected by pH. If the conjugate acid is an anion of a weak acid, it will. Well, good. So if a substance has a basic anion, right, those weak bases, it's going to be soluble in acidic solution because it's going to produce some weak acid. I feel like I need to take that bullet out. Buffer issues. Yes, if I did have this is a weird question. Okay, if I did have a buffer solution in here, then I would have, it would be fine because I'd have HA and F already, so I'd have plenty. Okay, so let's not worry about that too much, but let's go on. So let's do these practice problems. So basically what we're going to do is decide, do my anions, will they be affected if I have, will they be more soluble in acidic or basic solution? So here I have, whoa. Hello? No. Okay, for A, I have nickel, whoops, hydroxide, nickel 2 hydroxide. Whoops, it's gonna go into nickel 2 plus 2 hydroxides. So let's just think, if I add, so it says, which substance is more soluble in acidic or basic solution? So let's just assume, if I have acidic solution, let's think about Le Chatelier's principle. If I have an acidic solution, so I add a bunch of H pluses over here, what happens to the hydroxide? Do I add more hydroxide? Do I take out hydroxide? What are you saying, Stephen? Unmute.
Is it take out hydroxide?
Yeah, because I'm forming water, right? So now I'm forming water, so I'm removing hydroxide. So which way am I going to shift if I remove hydroxide? To the right or to the left? This could be anybody. If I remove something, which way do I move?
To the right.
To the right. I have to replace it now, right? So I'm gonna get rid, now I have to make more of this nickel hydroxide dissociate because I need to make more hydroxide. So is that increasing solubility or decreasing solubility if I'm removing more of it, if I'm dissolving more of it?
Increase.
Increase. Good one. Yes, it is. It is an increase. I'm basically I'm removing hydroxide and I'm forcing more nickel hydroxide to dissolve. So this is more soluble in acidic conditions. Let's say I did have hydroxide, right? If I added hydroxide here, maybe I'll actually put that over down below. Let's say I added a bunch of hydroxide. Now I'm doing common ion, right? Now I've added extra product. So that's going to force me to shift over here and get rid of nickel and hydroxide. So I'm going to actually make that less soluble. So if you make more of your salt, you're less soluble. If you dissolve more of your salt that way, you're more soluble. Okay. So let's try B with calcium carbonate. So if I have calcium carbonate, I'm going to make calcium and carbonate. So let's just see so is carbonate a conjugate base of an acid? I got a nod from Marcus. Yep, it is. Carbonate's actually super basic. It's what makes the bubbles of the volcano reaction when you mix it with vinegar, right? So if I add hydrogen ions here, am I going to have a separate reaction? Yes, the answer is yes. You will. You'll actually have H plus carbonate going. You actually get two H pluses, end up making water and carbon dioxide. Funnily enough. And we learned that back in the gas chapter phase of like chapter 8. But either way, even if you don't know that, this subreaction, you should know that carbonate, right? Carbonic acid is an acid that we're familiar with. And so if we have hydrogen going with carbonate, we're going to get bicarbonate at the very least. So we are going to pull it out. So if I have hydrogen, am I removing carbonate? Yes, I am. So I'm removing carbonate if I add acidic conditions. So I'm going to have to make more calcium carbonate dissolve to replace it. So this is increase the solubility in acidic. If I add hydroxide, is hydroxide a part of this process at all? Do we see hydroxide? No. So I would actually assume that it wouldn't have any effect if hydroxide was added. So no effect in a basic solution, but acidic solution for sure. Okay, let's switch the color. Okay. C. Barium fluoride. Oops, solid. Good. Going to barium, bringing it back to our first example. Plus 2 fluorides. We're just going to start with hydrogen again, because why not? Now, are either of these ions conjugate bases of weak acids? Yes, it is. Just like carbonate was a conjugate base of a weak acid, Fluoride is a conjugate base of weak acid. So if I add or H plus in here, am I gonna have a reaction? Yep, I'm gonna have fluoride plus hydrogen. It's gonna react to form HF. Right, it's gonna have a separate equilibrium reaction. Pulling it out. So what's gonna happen to my solubility? Oh, good, Emery. Increase. Increase solubility in acidic with an acid. Okay. Now if I add hydroxide, I'm going to be adding a strong base to a weak base. No effect. Okay, now last one. Silver chloride. So it goes to silver ions. Oops, aqueous. Plus chloride ions. Okay, so now is chloride a conjugate base of a weak acid? What kind of acid is HCl?
Strong.
Strong acid. So that makes chloride what? What kind of base is chloride then?
Negligible.
Perfect, negligible. So if I add hydrogen ions to this, will it do anything? Unfortunately, fortunately not. Nope, it won't do anything. So that one will have no effect with that. Now let's think if I add hydroxide, will it react with anything? It's not going to draw it out. So it might have a separate reaction to make silver hydroxide, but it's not going to affect the solubility within that one. So no effect. So basically, if you find a conjugate base of a weak acid or of a strong acid, no effect with pH. Okay. Cool. Okay. I know we only have a few minutes left, so I want to hustle through this. I'm sorry. So transition metals, we talked about them being good Lewis acids because they're going to bond with the water molecule and make that, they're going to make a complex. So that complex makes them more acidic because those attached waters can dissociate their hydrogen ions a lot easier. So a complex ion, I kind of think of it as the reverse of solubility. Instead of having a one thing here, let's say it's like, right, I had mx going to m plus and x minus. Now I have m plus and x minus going to form a complex ion, but now it's aqueous. So these complex ions, it's basically a cation attached to either a bunch of anions or neutral molecules. And some of those ions could actually be water. So here's silver. What's the charge of silver? +1. And then water is neutral. So even if I add 2 waters onto here, silver is still going to be +1. So the charge of this whole ion is whatever the charge is of my cation. The attached ions are called ligands. So the thing that attaches to the metal. So water is the ligand here. And when we form some of these, so basically the last section we talked about pH, right? How that affects the base part. This is what affects the cation part. So if I form a complex ion, I'm taking some of my cation and I'm doing a separate reaction with it. So this will happen if my ligand forms a stronger bond to the metal than I had before. So here, if I have silver dissolved in water, I have, right, it's hydrated. We call it, right, the silver is kind of attacked by the waters, and that's dissolved. But if I put ammonia in here, that ammonia has a stronger affinity to the silver than water did, and it will replace it. So then I get these silver ammonia complexes. And so water basically gets kicked off. And so we don't normally write water, right? And when we write aqueous, so we don't normally write these waters attached, even though they technically are, right? They're always attached. So we would just write the other things that are not water. So silver aqueous, where that's the notation that there is water on it, plus ammonia dissolved in water, producing ammonia, this like diamine silver cation. So K here is still products over reactants, but now we call it KF for the formation constant of a complex ion. So again, we'll still be dealing with products over reactants, still raised to the powers and such. So products over reactants. Here are a bunch of KF values for a variety of complex ions. Notice aluminum has a charge of +3. So if I have 6 fluorides on there, I have a +3 and then 6 minuses. So then my overall charge of this ion is 3-. Now these KFs tend to be positive numbers because we tend to make a lot of them, right? Because they happen to form. So we're going to have more products and reactants. So they tend to be large, where a KSPs tend to be really small. So silver chloride is very insoluble, has a KSP of 10 to the -10. If I put ammonia in there, then the silver will bind with the ammonia groups. And then I will actually switch my, I'll shift my equilibrium to dissolve actually all of that silver chloride. So then I have silver ammonia complex in here and then a bunch of chloride ions hanging out. So that's what that overall reaction looks like. Okay, we're gonna end there today. Let me see what I have left. Okay, we have 1, 2, 3, 4. A few slides here left. So on Wednesday, we'll finish these slides and then we'll do titrations. So the quiz on Wednesday will just be on this stuff up to what we just learned. Do you guys have any questions before we end? Make sure you do your attendance. Make sure you're here on Wednesday to turn in your stuff. If you're worried about that, please let me know.
Thank you.
You're welcome. Sergio, good to see you. We need to talk, dude. Oh my God. We're going to talk. Stay here.